For centuries, humanity has looked into the night sky believing that everything we could see, every star, every galaxy, every glowing cloud of gas, represented the universe itself. But modern astronomy has revealed an astonishing truth. The visible universe may account for only a tiny fraction of what actually exists. Hidden beyond the reach of ordinary telescopes is an invisible cosmic framework that silently controls the motion of galaxies and shapes the largest structures in existence. Scientists call it dark matter, yet despite decades of research, no one has ever seen it directly. To investigate this invisible universe, the European Space Agency launched one of its most ambitious observatories ever built, the Euclid Space Telescope. Unlike telescopes designed to capture dramatic close-up images of planets or colorful nebulae, Euclid has a very different mission. Instead of focusing on individual objects, it is surveying enormous regions of space, collecting information from millions of galaxies at the same time. Positioned nearly 1.5 million kilometers from Earth at the Sun-Earth L2 point, Euclid operates in a remarkably stable environment, free from many of the disturbances that affect observations closer to our planet. From this distant location, it can continuously scan the sky with extraordinary precision. Its mission is ambitious. Over several years, Euclid will create one of the largest three-dimensional maps of the universe ever assembled, covering more than one-third of the entire sky. To accomplish this, the telescope combines visible light imaging with infrared observations. This allows astronomers not only to see distant galaxies but also to estimate their distances and measure how they have changed over billions of years. But perhaps Euclid's greatest strength lies in something far more subtle. As light from distant galaxies travels across the universe, it passes through massive concentrations of matter. Gravity slightly bends that light, stretching and distorting the shapes of background galaxies. These tiny distortions are almost impossible to notice individually, but when millions of galaxies are analyzed together, they reveal an invisible map of where mass is actually located. This phenomenon, known as weak gravitational lensing, gives scientists one of the most powerful tools ever developed for studying dark matter. Instead of observing dark matter directly, researchers can detect its gravitational influence, allowing them to reconstruct the hidden structure supporting entire galaxy clusters. Even Euclid's earliest observations demonstrated just how powerful this approach could become. Its first large sky images revealed breathtaking fields containing millions of stars and galaxies packed into a single panoramic view. Regions that previously appeared almost empty suddenly became filled with countless faint objects that older surveys had missed. Many of these newly identified galaxies are extremely small and dim, making them difficult to detect with previous instruments. Yet these tiny systems are incredibly important because they respond strongly to the gravitational pull of surrounding dark matter. By studying their distribution and motion, astronomers gain valuable clues about how invisible matter has shaped the universe for billions of years. Euclid has also begun examining nearby galaxy groups and ancient stellar populations with remarkable detail. In several well-known regions of space, the telescope detected faint stars that had remained hidden among brighter neighbors, providing astronomers with new opportunities to study how galaxies formed during the early history of the cosmos. Each new observation adds another piece to an enormous cosmic puzzle. Instead of viewing galaxies as isolated islands scattered randomly through space, Euclid is revealing that they belong to something far larger. As scientists combined observations from different regions of the sky, an extraordinary pattern became increasingly clear. Galaxies gather along gigantic filaments stretching across hundreds of millions of light years. These immense structures intersect at massive galaxy clusters while enormous empty voids separate them. Together, these interconnected filaments form what astronomers call the cosmic web. Although stars and galaxies make this web visible, researchers believe its true backbone consists almost entirely of dark matter. In other words, the glowing galaxies filling the night sky may simply trace an invisible structure that has existed since the earliest stages of cosmic history. Every new image strengthens this remarkable picture. Rather than discovering an entirely new universe, Euclid is revealing one that has always been there, but remained hidden because humanity lacked the tools to see its invisible architecture. And this is only the beginning. The telescope has surveyed just a small fraction of the sky it plans to observe. As billions more galaxies are added to its growing map, scientists hope to uncover even deeper clues about the mysterious forces shaping everything we see. If mapping the hidden structure of the universe sounds ambitious, Euclid's ultimate objective may be even more extraordinary. Beyond revealing dark matter, the telescope is designed to investigate one of the greatest mysteries in modern physics: dark energy. More than 2 decades ago, astronomers made a discovery that completely changed our understanding of the cosmos. Instead of slowing down under the force of gravity, the expansion of the universe is actually speeding up. Something unknown appears to be pushing galaxies farther apart with increasing speed. Scientists named this mysterious phenomenon dark energy, but the name does not explain what it is. In reality, nobody knows its true nature. It could be a property of empty space itself. It might represent an entirely new field of physics. Some researchers have even suggested that our current understanding of gravity may be incomplete on the largest cosmic scales. This is where Euclid becomes incredibly important. Over the course of its mission, the telescope will observe billions of galaxies spread across more than 10 billion years of cosmic history. Because light takes time to travel, every distant galaxy acts like a snapshot from the past. The farther away Euclid looks, the further back in time it can observe. By comparing nearby galaxies with extremely distant ones, astronomers can reconstruct how the universe has changed over billions of years. If the rate of cosmic expansion has varied in unexpected ways, Euclid's enormous survey may reveal those subtle differences with greater precision than ever before. The telescope is also expected to improve measurements of one of astronomy's most powerful tools, gravitational lensing. Every tiny distortion in galaxy shapes contains information about the invisible matter lying between Earth and those distant galaxies. When billions of these measurements are combined, researchers can build an incredibly detailed map showing where dark matter is concentrated throughout the universe. These maps may answer questions that have challenged astronomers for decades. How did the first galaxy clusters grow? Why are some regions packed with galaxies while others remain almost empty? And does dark matter behave exactly as today's theories predict? Some early analyses have already hinted that certain large-scale structures may have formed differently than expected. These results are still being carefully examined, and scientists are cautious about drawing conclusions. That is exactly how science works. Extraordinary observations require extraordinary evidence, and every new discovery must survive years of testing before it becomes accepted. Even so, Euclid is already providing researchers with an unprecedented amount of information. The mission is expected to generate one of the largest astronomical data collections ever assembled. Processing such an enormous archive is impossible through manual inspection alone. Instead, advanced computer algorithms and artificial intelligence help identify faint galaxies, detect subtle gravitational signals, and search for patterns that human eyes could easily overlook. Rather than replacing astronomers, these intelligent systems allow scientists to focus on interpreting discoveries that would otherwise remain hidden inside mountains of data. As Euclid continues scanning the sky, its three-dimensional map will steadily become more complete. New galaxy clusters will emerge. Previously unknown dwarf galaxies will be identified. Ancient galaxies from the early universe will help researchers understand how the first large structures evolved after the Big Bang. Each new release will refine our picture of cosmic history. Perhaps the most remarkable realization is not that the universe has suddenly become stranger. It is that the universe has always been this complex. For generations, humanity observed only the brightest stars and galaxies, believing they represented the whole story. Now we know they are only the visible surface of something vastly larger. Invisible dark matter shapes galaxies. Dark energy influences the expansion of space itself. Gigantic cosmic filaments stretch across unimaginable distances, connecting clusters of galaxies into a structure unlike anything once imagined. Euclid is allowing us to explore this hidden architecture with a level of precision that was impossible only a few years ago. And the mission is still in its early stages. Most of the sky remains to be surveyed, meaning the greatest discoveries may still lie ahead. Whether Euclid confirms today's theories or uncovers evidence that forces scientists to rethink the foundations of cosmology, one thing is already becoming clear. The universe is far more intricate, more connected, and more mysterious than humanity ever believed. Every new observation brings us one step closer to answering one of the oldest questions ever asked. What is the universe really made of?